Okay, hello. My name is Matthew Mazzatano. Today I'll be discussing my lab 2, which is where I observe the motion of a falling object which has no forces acting on it besides the weight and the drag force due to air resistance. By observing the motion of the ball, we observe Newton's second law of motion. I recorded the ball being dropped from rest and tracked its motion using a computer program and recorded the position of the ball over time. I then programmed the ball's position over time using a Python code and a simulator to create models with and without the effect of drag, air resistance. Finally, I compared the predicted models against my observed model. So here's a screenshot of my tracker program. So you'll see that I marked the position of the ball at each individual frame in the video to create data for the position compared to time. So in my tracker program, the mass of my ball was 1.81 kilograms. I used my height to accurately measure the distance the ball traveled, which is 1.85 meters. I placed the origin of the coordinate system at the center of the ball at frame 0. I tracked the position of the ball by placing a marker, which were these blue diamonds seen here, at the center of the ball each individual frame, and then using the distance calibrator to find its position accurately. So in glow script, we'll see that I updated delta t, did all these things. I'll show you. So the mass of my ball here is 1.81 kilograms. The initial position of my ball is at 0, 0, 0, which is true. There was no initial velocity because I dropped the ball from rest. Here, delta t is the size of each, the length of each frame in the video, and time starts at 0. The magnitude of gravity is 9.8. And here b, which is the magnitude, the proportionality constant for the magnitude of the drag force, which is an arbitrary number. I had to guess and check that because, I had to guess and check that until the simulated model was similar to my observed model. So for the while loop, I set the interval to match the length of my video. Here the weight force is equal to the negative mass of the ball times gravity times the unit vector. It's negative because the force of gravity is pointing in the negative y direction. Here's the force of drag. Here's the proportionality constant times the square of the ball's velocity, which is discussed here. The magnitude of the drag force is proportional to the square of the ball's velocity, so I implemented that into my code using this line here. And I updated the ball's velocity and the ball's position using these two lines of code, and was able to finally create a simulation and data of my ball's position over time, using with drag and then without drag. Okay, here is a graph of my ball's position over time and the simulated models of the position over time. So we'll see initially here that the white square, which is the simulated without drag, it has a steeper slope, which means that it has a higher velocity. Because there's no drag affecting it, it's able to go a faster velocity, a higher velocity. You'll see that my observed model went the slowest initially and over time, and only until about the last half second or so, or not half second, 0.1 second, was the observed velocity similar to the simulation with drag, which was supposed to represent something closer to real life, how the ball would fall in real life. And then, so what if the ball was thrown downwards instead of released? Well, the magnitude of the terminal velocity would not be different than if the ball was released. The terminal velocity will always be the same for the object. Doesn't matter if it has initial velocity or not. As soon as the force of gravity is equal to the drag force, the ball will have reached terminal velocity, but it will be reached sooner for the thrown ball if the ball is thrown downwards. We can see this through my models because drag force is proportional to the velocity, to the square of the ball's velocity. Okay, thank you.